Hello and welcome to today's lesson on the principle of moments. In this lesson, we'll understand and explore the principles of moments. We'll then visualize the principle of moments by exploring the example of a seesaw at the playground. Finally, we'll work through some cases of applying this principle to consolidate your knowledge. So far, you have learned the equation moment equals force times distance. You are also familiar with real-life examples of moments. Building on this foundation, understanding the principle of moments will deepen your grasp of how forces and turning effects work together in real-world scenarios. This knowledge advances our understanding of physics by showing how balance and equilibrium are maintained in systems around us. Let's get started. The principle of moments states that for an object to be in equilibrium, balanced and not rotating, the total clockwise moment about any pivot must be equal to the total anticlockwise moment about that same pivot. In simpler terms, if you have a seesaw, to keep it perfectly level, the turning forces on one side must balance the turning forces on the other side. This is crucial for understanding how balance and equilibrium are maintained in physical systems. It is important to remember that the moments acting on an object only correspond to the rotational movement that the object experiences. If the moments are balanced but there is still a resultant force acting on the object won't rotate but may move in a certain direction based on the rules of forces we have learnt in previous lessons. But if both the forces and the moments are balanced, the object will neither move nor rotate. To better grasp this concept, we'll introduce the idea of a couple. A couple consists of a pair of forces that are equal in magnitude but act in opposite directions and do not cause any linear motion. Instead, they create a turning effect or moment. Imagine trying to unscrew a jar lid. You exert force in one direction with one hand and an equal force in the opposite direction with the other hand. This pair of forces creates a turning effect but doesn't push or pull the jar sideways. The classic example to illustrate the principle of moments is a seesaw at a playground. Suppose two children of equal weight sit at equal distances from the pivot, one on each side. Here, the clockwise moment created by the weight of the child on one side is balanced by the anti-clockwise moment created by the weight of the child on the other side. As a result, the seesaw remains perfectly level because the total clockwise moment equals the total anti-clockwise moment. Hence, the seesaw stays balanced and stationary. To put it into perspective, if one child moves closer to the pivot, the distance decreases, and thus the moment decreases. To balance the seesaw again, you would either need the child to move back to the original position, or the other child would need to adjust their position to match the first child. Let's apply what we've learned to a few specific problems to consolidate our new knowledge. Imagine a beam balanced on a pivot with unequal masses placed at different distances from the pivot. The beam is in equilibrium and you need to find the unknown distance. First, figure out what information we've been given. So we know that mass 1 is 10 newtons and is located 2 meters from the pivot. We also know that mass 2 is 20 newtons, and we need to determine its distance from the pivot D. Next, we need to calculate the moments. Starting with the moment of mass 1. We plug the numbers onto our formula, giving us 10 times 2. Therefore, the moment is 20 newton meters. We know to balance the beam, the clockwise moment should equal the anti-clockwise moment. Therefore, the moment of mass 1 should equal the moment of mass 2, and as we have just calculated, the moment is 20 newton meters. We can put this into our equation, giving us 20 newton meters is equal to 20 times d. Then we can solve for distance by dividing both sides by 20. Therefore, d is equal to 1 meter. So, mass 2 should be 1 meter from the pivot for the beam to remain balanced. Let's look at another problem involving a seesaw, similar to our initial example, but with different weights and distances. So looking at the given information, we have a child weighing 500 newtons sat 0.5 meters from the pivot. We also have another child weighing 450 newtons. We need to determine its distance from the pivot to balance the seesaw. Now we need to calculate the moments. Starting with the moment of child 1, we plug our known values into the equation. So we have the moment of child, 1 is equal to 500 times 0.5, this equals 250 newton meters. We know for equilibrium, the moments should be the same, so we can input our known values into the formula. So we have 250 is equal to 450 times by the distance. Now we solve for distance by rearranging the equation, giving us 0.56 meters. So the second child should sit 0.56 meters from the pivot for the seesaw to be in balance. By working through these examples, you see how the principle of moments allows us to solve various real-world problems involving balance and equilibrium. This not only illustrates the principle itself, but also shows its utility in many practical applications. Through this lesson, you've learned that the principle of moments is essential for ensuring balance and equilibrium in systems. By understanding that the total clockwise moment about a pivot must equal the total anticlockwise moment, you can predict whether an object will stay stationary or not. Adding the concept of a couple shows how forces can create rotation without linear motion, deepening your understanding of how forces interact in the real world. Watch the rest of the GCSE physics course at Sophos Education.